Inshallah, as I said, we will make a demonstration for this heat exchanger, including the tube bundle assembly, tube sheet hauling. As I said from minutes, all of us knows that a modeling like this may take between 4 and 6 days to make the complete model and detailed drawings for this heat exchanger. Inshallah, during this training today, we will make the demonstration and in detail for this type of heat exchanger. And here, as you can see, we prepared the tube hauling, including the baffle impingement blade for the inlet nozzle, the expansion joint, and in this training, inshallah, we will learn how to import an external files, how to make helicide nozzles, how to make nozzle rips, how to make a custom part like this part, which is not included in SEG library, how to create something like that and use it inside SEG library. Okay, let's start, inshallah. We will make a new project. This project we will call it demo. Select the project location, and from here we will select the heat exchanger as the module that we will use for the static equipment. This module will give you the ability to create tube sheet and the tube sheet hauling tube pattern. Okay. Now from here, as we discussed on the previous session, how you can make, how you fill the project information, and from here how you fill the design data, and how you can edit the equipment setting, and if you have a large diameter vessel, how to define the delivered blade dimensions to use it on the circumference, the diameter or length, circumference length of the chord length of the shell. Now let's start creating the model of this heat exchanger. Here we can divide the heat exchanger in 3 parts. The first part here is the front end, and here on the middle we have the shell side, and the bonnet at the end as rear end. Okay, let's start from here. We will create the first part, which is this ellipsoidal head. After that, we will create this shell and this type of flange. From here, let's open SEG Software, and from elements, let's add the first part, which is left head. And from here, let's define the dimensions of this head. As defined here, this head is a tropospherical head, okay, with defined crown and the neck radius. So we will select from here the user defined crown and the neck radius. After that, we will define the dimensions of this head, the thickness and minimum thickness after forming. And from here, let's define the crown and the neck radius 852, and this is 85.2, and let's click save. Now we define this head as a tropospherical head. If we open the bill of material, we can find the description of this head as a tropospherical head. Here that's the inside diameter, thickness, and the minimum thickness after forming. Straight flange length, we will define that to 50. That's a crown and the neck radius, so let's define the straight flange length and click save. Now let's add the second element, which is this can, okay, with that length. Okay, so let's add the second part, which is CAN1. And from here, we will select CAN1 as the shell type, define the inside diameter, the thickness, the line orientation, and length of this element. And now let's add the third part, which is design the flange. So let's add F1. Okay. And from here, let's select the suitable type for our case. Here you have a list of design the flanges. The suitable type for our case, which is loose ring flat face. If you take a look to the image on the right hand side, it looks like flange from plate, no raised face, like here on the detailed drawing, which is this type of flange. So the suitable type in this case, which is loose ring flat face flange. Let's define the dimension. The inside diameter will be the shell outside diameter. Okay. Here the flange outside diameter. Flange thickness. The bolt circle diameter. The hole diameter. And the number of bolts. And here if you have an offset, but in our case no offset, so we will make this value as 0 and click save. Now let's create the assembly for those three parts. Here we have the first cap, the first shell, and now we have the body flange as loose ring with flat face. Okay, now let's add some more parts. Here we have between the tube sheet and this flange, we have a gasket here. And this gasket is including a bus partition. So we will learn two ways to make those bus partitions on the gasket, because the available gaskets on the bus partition not include a holing for bolts. But here on the rear type of gasket, this type include holing like that one, which is user-defined rest face gasket with bolts. So we will define this type like that. Bolt circle diameter, hole diameter, and the number of bolts. Now let's click save. After that, let's add the tube sheet. So from here, let's add and from here, let's select the fourth type, which is tube sheet gasketed from one side and welded from the other side and extended as a flange, which is that type. Okay, so from here, let's define the dimensions of this tube sheet. The bolt hole diameter and number of bolts. And from here, let's select the bus partitions. So to know the bus partitions that we need from here, I will select that type right now. And from the help, if you click on the help button, you will get this this help. And if you come down here like that, and if check this page here for the 6 passes bus partition as mentioned here on the drawing, we have 6 passes. Okay, so and the bus that we will use, which is segment type. So from here I select the segment type. So let's close this one. So from here I select the segment opposite direction, and from here we will define the values of top and the bottom offset for the bus partition after calculating the tube bundle arrangement. So from here, let's click on save, and from the tube bundle, we will modify the or define the tube bundle arrangement. Okay, so from here, let's create an editing and define the dimensions of tube in millimeters. 50. Let's accept that. And for the top clearance, 100. For the top clearance, 100. For the tube passes, we will select the 6 passes, which is that type, and make the passes arrangement vertical and symmetrical. And from here, you can select the tube bundle arrangement and the big point to the center of the vessel or not. Now let's start creating the bus partition arrangement, and from here you can get the number of passes per each partition. So let's move this pass down a little bit, and from here we will get this number of passes. So we have here 46 tubes and here 49, and that's the pass partition clearance. Okay, so let's close this. So 98.576. So from here, let's define that one to be like that, and same as the bottom. And let's click on save. Now let's click run the assembly to create the gasket and the bus partition. Okay, now we have that bus partition. Let's open it. Okay, if we go to that facing, you will get this bus partition location. Okay, now let's complete the as we said, we didn't save the tube pattern arrangement. We will come back after creating the main body of the exchanger. After creating this tube sheet, we will proceed with can 2, which is this can. We have a can here, and that can length is 1.5 meters. So from here, let's open SEG and can 2, and from can 2 we can make it looks like can 1. Okay, like that, and you will need to make a refresh and come back to the node, and from here we can define the thickness, and from here we can define the longitudinal welding line orientation and the length of this shell 150. Let's add another can 3, and let's make it looks like can 2 to avoid repeating data entry. Just to change the longitudinal welding line orientation, let's add another can, which is can 4, and let's make it look like can 2 here, and from here here that's the second can, and that's the third can 553. So from here let's change the length 553 and save. After that, we have an expansion joint. As per this drawing, we have an expansion joint here. Actually, this expansion joint or this type of expansion joint not available in SEG. So how we can deal with that and import it inside our model? And as I can see here, it will be supplied by another. So we can do the following. Here from that detail, we can create a part like that. If we open it from to disk inventor here, let's go to the workspace and open the expansion joint. Here we create this part as a custom part. Okay, it's a part, not assembly, and we will use it in our assembly as an external reference. And you should know that you should have a start UCS and end UCS. As we discussed on the previous session, that to make an assembly in SEG, the main parts need to have start UCS and end UCS with those characters. Start space UCS and start word starts with a capital letter. And UCS, all characters are capital letters. The same for end UCS. So we add an end start UCS at the start of the this connection, and add an end UCS at the end of this connection. Now, how we can import it in SEG? Let's start the assembly to start creating CAN 2, 3, and 4. After that, we will import the expansion joint. Okay, now we will come back to SEG, and from Elements tab, let's select the vessel, and from here you will find a button called Custom Part. So from here, from Custom Part, we will need to close all open documents. After that, from here, we will select the file which is located on this folder, which is the expansion joint. So we will select it from here and give it a name, which is expansion joint. Okay, and from here let's load it. Okay, after loading, you can figure that the expansion joint weight here and the material, you can define the material here, and the description of this part, and the technical characteristic like slide and you can define the material as simply horizontal. Now we can append this part to our model by clicking on append. Now the expansion joint included to the project. Now let's add another part, which is this small can with that lens. Okay, so from here let's open SEG and let's add CAN 5, and let's make it looks like CAN 3, and from here we will define the CAN length to make it 2 millimeters. After that, we will add centric cone. This cone length is 270. So from here, let's come back to SEG and add centric cone from blade. So let's add cone 1. And from cone 1, we will select eccentric cone and start defining the dimensions. The start inside diameter, the thickness 10 millimeters, the longitudinal welding line orientation, the length of this cone, and the end inside diameter. Let's add another can, which is CAN 6, and from here let's select the shell type, and from here define the inside diameter to be looks like the can end diameter, longitudinal welding line orientation, and length. Let's add another cone, which is cone 2. and let's make it looks like cone 1. Okay, but here we will flip the sizes of the diameters, so it will be like that. So the large diameter will be at start and the small diameter will be at the end, like that case. So they are the same, but the start and end diameter are flipped. Now we have another can here. Okay, so let's add another can, which is can 7. So let's select the vessel, and from elements let's add can 7, and let's make it looks like can 2. Okay, here we have the longitudinal welding line orientation 3150, so it will be 45, and here the longitudinal welding line, the length of this can is 170, and let's click on save. Now we will add the second tube sheet. Okay, so from here let's add tube sheet 2, and let's make it looks like tube sheet 1. The same information, but from here we will make the pass partition as 4 passes. Okay, not 6 passes, because as you know, here if we open the help again, sorry, I will show you it on the gasket. So after saving this tube sheet, we will just make it flipped, we change the bus partition and change the direction of the tube sheet and make it flipped. Now let's create the tube pattern and the tube hauling. So from tube bundle, let's delete the tube bundle folder from the project. So from here, let's delete this bundle folder, and from here let's start creating the assembly, the remaining items. Okay, now we have the main body of the heat exchanger, and now let's let's close the project and open it again. So from exit, let's close this project. Okay, and let's close Autodesk Inventor. Maybe some elements stuck on the memory, so let's Control V. Let's open any instance. Open from Autodesk Inventor. Check if there is any instance. It's opened. So now let's run Autodesk Inventor. Okay, and let's run SEG. Let's open the project. Now let's modify the information of the tube bundle. Tube clearance, and from here you will make the clearance. Select the number of passes, make them vertical and symmetric, and from here, from draw, we will start drawing, and we can move pass partitions up and down. We will accept that by exporting the information from this button. Okay, now those data are saved inside a JSON file here in this project. If you open this folder, which is tube sheet bundle, you will find a JSON file here. If you open it with Notepad, you will find a file here including the information of all the tube bundle assembly. Okay, now let's add tubes and baffles to this tube sheet. So from here, let's add a tube, and from this tube, let's select a user-defined tube. And if we open the project, so let's open the assembly from here. If we make this, if we take a section and measure the required length for the tube from inspect, and from here, if we measure the distance from this face and that face, that's the length of the tube, and we will add 6 millimeters plus, which is the extent of the tube from this side, and 3 millimeters extend from that side. So the total length of the tube will be 6538, and let's click on save. Now let's add baffles. So as per this drawing, we have a baffle here, and this baffle is patterned 4 times. Okay, so from here, let's add B1, and B1 dimensions to be like this. That is the inside diameter of the shell, and that the cut, which is the cut on the baffle, and that spacing between baffles, the thickness of the baffle, clearance between the baffle and the shell inside diameter, location of this baffle, and the orientation of the cut. And from here, we will make a vent hole at the bottom, and the pattern we have 4 baffles. Let's add another baffle, which is B2, and let's make it looks like B1, but we will change the location of this baffle and the orientation. So the location will be like that, and the orientation will be like that, and we will remove the vent hole and the same pattern. Okay, so now we have here baffles up to here. Now we have another 2 baffles, baffle on the large diameter. We have 2 baffles on the large diameter. So from here, let's add another baffles, which is baffle B. Okay, and from baffle 3, let's define the inside diameter, which is the large diameter of the shell, and here the baffle cut, and here the spacing between baffles. This value is not important because we don't have a pattern, it's just 1 baffle, so this value is not important. Clearance and the location of the baffle and the orientation, and we have a hole at the bottom. And let's add another baffle, which is baffle 4, and baffle 4 looks like baffle 3 but with different location and orientation. So from here, let's change the location of baffle B, baffle 4, and the orientation of this baffle, and let's remove the Now let's create those items. Here we have the first tube. The first baffle was better. The second baffle was better. After that, we have the third type of baffle and the fourth type. Okay, now we have those items of the baffle. We will proceed with tube pattern assembly and hauling. So from here, we will select the tube sheet. And to start hauling, we will need to open the tube sheet hauling form and just click on start hauling. Here in this form, you will find the location of each hole and the diameter of each hole. And just click on start hauling, and SEG will proceed with hauling. First, SEG will check the items before hauling, check if it exists and without errors or not. After that, we'll proceed with creating sketches for tube locations in X and Y. After that, we'll create a hole. If we take a look at this tube sheet here, as you can see, SEG start creating tube hole locations as sketches as we create on the tube pattern arrangement, and now the tube hauling created. On the second tube sheet, the same thing. And the tube hauling is done. Now the pattern for tubes. Here the location of tubes. After that, the pattern will done for the tubes. Here we have the pattern of the tubes. Now the hauling of the baffles will proceed. The second baffle hauling. After that, the third baffle hauling. As you can figure, all of that, if you make it by hand, it will takes a huge time to manage something like that. But with SEG, as you can figure, it takes just a minute to handle this, to create the tube bundle arrangement. After creating this tube bundle, we will proceed with the other parts, and at the end we will come back again to the tube bundle to add the tie rods and the spacers. By the way, you can add the tie rod and ceiling rod from the tube bundle assembly itself, but here we have short tie rods and long tie rods, and I preferred to discuss in this training how to add something like that by hand if you would like to make it. Okay, you can do it by SEG, but with one length only for long or short tie rod, and the second one you will create it by hand. But here I preferred to make both by hand to show you how you can deal with that on the model. Let's complete the model. Let's add a pass partition here. A pass partition let's add a gasket here. After that, so at the end here we have a gasket. After that, a body flange, shell, and ellipsoidal head or spherical head. So let's come back again to SEG, and from here let's select the visit, and let's select gasket with pass partition. So let's add G2, or gasket number 2. And from here, let's select 4 passes, and you can figure from here the shape of the pass partition. In case of, if let's select the 6 passes here, which is opposite front end, you can figure that that's the shape of the pass partition. Okay, and that's for the rear end. So from here it looks like the 4 passes and rear side. So from here let's define the inside diameter, thickness, and here the width of the gasket, the thickness of the pass partition, and the fillet, and from here the four passes, that one, which is the front side, sorry, because we need to define the front side. Okay, so let's define the side diameter, thickness, gasket width, and here offset, the same offset of the pass partition, and the fillet. Let's click save. Now let's add the body flange, which is that one. It looks like the first body flange, which is F1. So from here let's add F2. Let's add a design flange F2, and let's make it looks like F1, but we will flip the direction of this one to make the facing to the direction of the gasket. After that, let's add the last can, which is that can, okay, with that length. Okay, so let's add the last can. So let's add can 8. Okay, and let's make it looks like can 1. But from here we will change the longitudinal welding line orientation and the length of this can, and let's click on save. Now let's add the last element on the main body of the exchanger, which is the right. And it looks like the left hand, so we will select the checkbox, and the same we will just flip the direction of this head. Now let's create the assembly to generate the those elements. That's the body flange. After that, the shell, and the last element, which is the spherical head. Okay, now we have this can here with the spherical head, and here that's the gasket. Okay, and that's the gasket with the pass partition. Now let's come back to the first element here and add the attachments. Here on this element we have 2 nozzles, N3, N2, and we have pass partitions here. So from here we will select can 1 from SEG and add a pass partition. So from here let's come back to can 1, and for the left head, on the left head we will add the bus partitions. So from here, let's select the left head and add a bus partition. So left head bus partition. And let's select the suitable shape for the bus partition, which is shape we have for the 6 buses. We have type A, which is not suits our configuration, and the type B, it suits our configuration. So we will select 6 buses type B and start defining the thickness, the end thickness, and the right extension. So the value of this right extension measured from, so let's get the inspector tool. The bus partition should start from here, okay, after adding the gasket up to here, that surface. So the length of this one should be 700 millimeters, because the gasket thickness will be 4.5. So from here, let's add the expansion, the chamfer, and the pin hole, and here the offset that we already get from equation for the cube arrangement. And here for the orientation, let's keep it 0 right now and check what is the configuration of this bus partition. So let's take another section to figure out the shape from another view. So let's take half section from here. As you can see, if we take a look from here, the bus partition need to be rotated with a 90 degree. So let's check that from here. So let's change the orientation with 90 degree and click on Start Assembly. So the bus partition location, as you can see, the direction of the bus partition not in the correct direction. You can see that we have that the bus partition location, but the bus partition, the cut of the bus partition is here, but the bus partition direction on the other side. So here we have an option for the other side. This option will flip the direction of the buses. So when you click on Save and click on Start, the bus partition blades will goes to the other side. So by that way, we rotate the bus partition to suit the orientation of the cut. After that, we flip the direction of the bus partition to suit the cut. Now we will add nozzles on this front end. So let's select can 1, and from can 1, let's add the first nozzle, which is N3. If we come back here, we have nozzle N3 at the top. Okay, and if we take a look here, that's nozzle N3, and here we have the projection. And if we go to the detail of nozzle N3, here we have this detail of nozzle N3, and here we have the reinforced pad of this one. So let's come back here and define nozzle N3, and from here this nozzle is a nozzle from plate. So let's select nozzle from plate connected to shell, and let's define here the outside diameter of the nozzle, okay, which is in that case 3 to 8.8, and thickness is 8 millimeters. Keep the longitudinal welding line orientation. Here the offset or the location of the nozzle, the orientation of the nozzle in 0 degree. And from here, it's not a radial nozzle, it's a heli-side nozzle. So we will remove the checkbox on radial and select the heli-side. And from here, we will define the offset of this nozzle. You can see here, offset of the nozzle is 200 millimeters. So that's the offset, and it's in clockwise direction. So we will keep that. And let's add a reband. We have a reinforced pads with 50 millimeter width and 8 millimeters thickness, and let's click on save. Okay, here if we come back to the general arrangement model and check nozzle N3 and N2 size, it's 12 inches. So from here, let's select the extension point of this nozzle and let's add a flange. So N3 flange. And from here, let's select slip-on flange. So from here, slip-on flange, the rating 150, the size is 12, and the offset, let's make it 15 millimeters, which is the offset from the facing of the flange to the pipe, and click on save. Now let's come back to the nozzle to define the projection of the nozzle. As per drawings here, if we take a look, here the projection is 700, so let's come back here, define the projection and save. Okay, now you can figure the projection of the pipe calculated automatically. Here you can define the weld of the nozzle, which will appear on the nozzle weld as we discussed on the previous session. Here that's N3. You can define the surface of this nozzle, the outside diameter, thickness, and here the weld style and the weld information, and here the pad information like thickness and width, and here the external projection and flange information, thickness like slip-on flange, and that's the rating of the flange and the facing of the flange. Okay, now let's add another nozzle, which is N2. So let's add N2 flange. Okay. As we discussed, if you make it looks like N3, you will lose the extension connection. So let's add it like that. After that, from here, let's make it looks like N3. And from here, let's add another flange, which is N2 flange. Okay. Let's click on add, and from here for the nozzle, we will modify the orientation. Let's make it 180 degrees, and for the flange, make it looks like N3 flange. Now we add those elements which the bus partition N3 and N2. Now let's create them on by SEG on Autodesk Inventor. As discussed on the previous session, if you would like to make a rendering for elements during creation, we have an option on the setting, give you this ability to make a rendering for elements during creation. So we can open it and change it if you would like. Okay, here we have the first nozzle, which is N3. After that, we have the second nozzle. Okay, so now we have this nozzle with reinforced pad as a nozzle from blade. So if we open this nozzle, for example, okay, and if we open this neck, the nozzle neck, you can easily get the flat pattern of this nozzle. Okay, and the same for the reinforced pad. If we open the reinforced pad, easily you can get the flat pattern of this reinforced pad for a heli-side nozzle like that. Okay, now let's complete data entry for this heat exchanger. If we come back to the model here, we have a saddle, okay, and have some nozzles here and there. So we will define those nozzles and this support saddle. Let's start with the saddle. This saddle located on the first can, so let's select the first can after the tube sheet, which is can 2. And from elements, let's add lift saddle. Okay. And from the lift saddle, as per drawings here, if we take a look here, we have the web on the left side, and this saddle with straight sides. So from here, let's select saddle with a lift rib like that. And from here, let's start defining the saddle. That's the contact angle, and here that's the height of the saddle, 1255. So here 1225.5, and that's the thickness. And for the wear plate, the contact angle, the width, thickness. Here for the base plate, that's the length, width, and here the thickness. So let's come back here. So that's and thickness, the whole diameter, and the whole offset from the long edge, and whole offset from the short edge. Here the location of the saddle. So let's come back here. So the location of the saddle calculated from the start point here, which is as we discussed on the previous session, it's start from the parent seam line, not from other elements. So we will remove the thickness of this tube sheet plus this groove. So from here, let's come back here and define the location of this saddle, like that, orientation and loss. So from that side, let's define some other values, and let's add outer ribs. The outer rib width like that, and we have mid rib. If we take a look to that one here, we have a mid rib. Okay, and let's click on save. Before that, we have a slot hole on this one. We have a slot hole on this saddle. So we will select this checkbox with the sliding holes and define the slot length as 30 millimeters. Okay, so from here, let's define the slot length to be 30 millimeters and click on save. Okay. Now, if we let's from the setting, let's make a preview for elements during creation and click save. Now, any element we will create, we will make a rendering for elements during creation. Yeah, Allah. Okay, that's the left saddle with slot holes. Now let's add another element. If we come back to the main drawing, we have a nozzle here. This nozzle is a heli-side nozzle with a cone connection, eccentric cone, and pipe and flange. On this nozzle, we have two other nozzles connected to this one, and we will use the technique of connection point as we used it on the previous session to add a nozzle to another nozzle. So from here, let's select CAN tool and let's add S1 nozzle. And S1 nozzle, if we come back to the table here, S1, yes, here it's 10 inches, okay, and the small diameter is 4 inches. Okay, so with the schedule ATS, so from here, so it's 10 inches, schedule ATS, and I think we have a reinforced bed. Yes, we have about 50 millimeters with 10 millimeters thickness, so we have 50 millimeters with 10 millimeters thickness. So the location of this one, and the orientation of this one will be as mentioned here in this drawing. It's on 90 degree with offset 293 millimeters. So from here it's on 90 degree, and we will remove the radial and make it a heli-side nozzle, and from here define the offset of this nozzle like that, and it's in clockwise direction, so the offset on the clockwise direction, so we will keep that as it is. And from here we will calculate the projection of this nozzle as per the drawings. It's 790, so that's the projection of the pipe. So the value here will be reflected here on the projection value automatically reflected here. Okay, we can add here a connection point to add nozzles to this. Let's create this nozzle first. Here we have this helicide nozzle, and we need to add two nozzles to this nozzle. They will be attached to it, which is nozzle N5 and N4. Okay, so as we discussed, to add nozzles like that, we need to add a connection point here. Takes the same properties of the pipe. So we need to add a connection point with 10 inches size, like a pipe, and the same scalable of the pipe. So from here, let's open the elements and add S1 connection point. And from here, we will select the suitable type for this one. Let's go down here and select connection point for nozzle as a pipe. Select the size, select the schedule, and click on save. Now we can add nozzles to this nozzle by using this connection point. So from here, let's add N4. And from here, N4, if we take a look to that one, N4 is 8 inches nozzle with that schedule and that rating. So from here, let's select 80s schedule, and the location, as we discussed, it will be with a negative value. Make it full on the nozzle, not outside the nozzle. Change the orientation, and let's add a flange to this one. By the way, you can define the surface of the nozzle here on this cell, and it will appear on the nozzle table. So from here, let's add a flange. This flange is a slip-on flange with the rating 150, the same size of the pipe, and let's click save. Now when we come back to the nozzle, we can define the projection of this nozzle to give us the projection which defined it here. We need an outside projection with 150. So if we come back here and type this value, so the projection here, the projection of the nozzle will be 150. So we will click yes, and let's add another nozzle to this connection point. So let's add N5. From here, N5 is 2 inches with the schedule ATS, and the location is the same location of the previous. So with a negative value, the orientation will be 170, and keep the other dimensions as it is. And from here, let's add a flange to N5 flange. And this flange will be slip-on flange 2 inches with 5 millimeters offset. And let's come back to N5 to define the projection to get a projection on the outside to be 150. So if we enter this value and click calculate, the projection will be like that. So if we click on start, here that's nozzle N4 assembly. Okay, after adding this nozzle, as we can figure, we have nozzle support here. Okay, and we need to add this support to the nozzle, and we will in the next step we will add this type of support and learn how to modify it. Now let's come back here and select the connection point again to add another attachment to nozzle S1. So from here we will select external attachments and select nozzle support rib, and let's add in the 5 ribs. Okay. And from here we have different types of ribs like that. If you have an elbow like that or nozzle like this, you can add a stiffening like that, but in our case we will add a stiffening rib like that. And here for that nozzle, if we can measure the outside diameter of the pipe with 2 inches, it's 60.3, so this is the same value here. And the rib width, which is the width of this rib, the thickness of the rib, and the rib angle, which is the tilted angle of this rib, and the location. It will take the same location of the nozzle with a negative value, the same orientation of the nozzle in the 5, and here the offset of this nozzle, let's make it 40 millimeters, and the projection we will add the nozzle projection, which is 150. The nozzle projection here. So the offset will calculate it from the facing of the nozzle, to that edge here, like this image here, which is the rib offset. Okay, and so let's add another ribs. So from here let's add another rib and select this one, and let's add another 4 ribs. Define the offset for each rib to make all of them the same, and click on save. Now let's click on start assembly to proceed creating the nozzle ribs. Now we have stiffening ribs for this nozzle like that. Okay, now let's add the other elements, which is the eccentric cone, pipe, and another slip-on flange. So from SEG, let's select the external connection point of the nozzle in S1. And from fittings, let's select standard cone, which is standard fitting, and select eccentric reducer. And from here, let's select standard eccentric reducer. It's 10 inches with a schedule ATS, bear 4 inches with schedule ATS, and from here let's click on save. Now let's click on start assembly. After creating it, we will check the orientation of this cone to make it suits the orientation. Here we need to make the horizontal line at the bottom. So if we so let's take a look here. You can figure that the horizontal line not at the bottom. So from here let's change the orientation of the cone and check it again. Okay, as you can see, it's become on the top, so we need to change it with 180 degree, so this value will be 90 degree. And let's add another element after it, which is another pipe. So this one pipe, let's add another pipe to this one, and this pipe will be the same pipe diameter, which is 4 inches and 80 is scalable, and the length will be 82. And let's add the last element, which is a slip-on flange. This one flange, okay, and this one flange will be a slip-on flange with 4 inches size and that offset. Okay, and let's click Start Assembly. The first we will define the orientation of the cone. After that we will create the pipe and the slip-on flange. Okay, now let's add another nozzles. We come back here, so we create that one, and now let's create nozzle 11, nozzle 10, and nozzle 9. Okay, so let's come back here to SEG and let's select CAN 1, which is a parent element, and from here let's add in 12. So here in 12, if we take a look to the nozzle table, it's 2 inches as a vent. Okay, so let's come back here, 2 inches ATS, and the location, and let's click on save. Let's add flange, so flange. Okay, and that one will be a slip-on flange with 2 inches, 5 millimeters. And from here, let's define the projection of this nozzle. Okay, that's the projection. Let's add another nozzle, which is N10. Okay, N10. After adding it, we will make it look like N11 and click on save. The same for the flange. Let's add a flange N10. After adding it, we will make it looks like N11 flange. And let's come back to N10 to change the location of N10. Here, that's location. Okay. And for N10, let's add a body flange gasket, and here we have a body flange connection to this nozzle. So from here, let's on SEG, let's add a gasket. N10. So it's 2 inches according to SMAB 16.5, and let's add a blind flange. And from here, let's select raised face blind, select N2 and make it flip. After that, let's add a stud bolt to this blind. So okay, so from here, let's select UNC bolt, and from here select the standard stud size as per the standard. So if we open that one and open the bolting flanges, if we take a look here to the 2 inches, okay, so the stud size is 5 by 8, and here for that one, so let's 85, and for the rating 150. So from here, let's make it 5 by 8, define length and flanges, and let's save. Now let's add another nozzle, which is N9. So from elements, let's add N9, and N9 it's the same. So let's make it like N11. Let's add a flange N9 flange, and let's make it looks like N11 flange. We will change the location of N9. So from here, let's change location, and let's click save. Now let's run the assembly. That's the first nozzle, which is N11. Second nozzle N10 with a flanged connection and the cover. The bolted connection. The third nozzle, which is N9. Okay, the flange size, I think we select the wrong size, so let's come back here, and from N9 let's select 2 inches, okay, and 5 millimeters. Okay, now let's add another elements. Here we have on the same part we have a trunnion and some of stiffening rings. We have a stiffening ring here, there, there. So let's add this trunnion first. So from here let's select can 2, and from elements let's add trunnion type 1. And from the trunnion, let's select the trunnion from pipe, not from plate, and the size is 6 inches as we're from here. If we take a look to the image here for the detail of the trunnion, here we have the detail for trunnion. Okay, we have a reinforced bad pipe and end plate. Okay, so from here let's define the schedule of the trunnion to be 40s as per drawings, the projection, and from here the location, same location, and the orientation. We have an end plate. The plate diameter is 200. It is 10 millimeters. The reinforced bad, it's the same dimensions. We have 2 trunnions. Okay, and let's click on save. After clicking on the assembly, nozzle N9 flange will be updated because it was 5 inches. We updated to 2 inches. Now it will be updated here. After that, we will create the trunnion. Okay, and here I have a note regarding the trunnion, because as per your drawings, when I checked the drawings here, the drawing diameter here, it was 250, which is the end plate diameter. not the rebad diameter as per this detail. If we take a look to this detail here, it is yes, that one. Here the drawn diameter on the GA, it was 250, not 350. So here, when you make the drawing of the 3D or the model of the 3D, you can figure that you have a clash between, or you need to approve the minimum distance. I think we have a clash here between the trunnion rebad and the saddle rebad. If you take a look again to here, the diameter here of this hidden line or dashed line here, it's for the outside diameter of the end plate, not the rebad. Okay, so here we can figure that we have an clash or interference between the trunnion rebad and the saddle rebad. Okay, let's complete that. We have some of stiffening rings here, 1, 2, 3, and 4. So let's modify them. If we get a detail for that, here that's the height of the ring and that's the thickness of the ring. So let's come back to the drawing, and from can to let's add stiffening rings. So from external attachments we will select external stiffening ring, and here let's add IR1. And from the types here, let's select the last type, which is the ring plate. Define the height, thickness, and the location of one. Add another ring, the same one, IR2, and let's make it looks like IR1 here, and we will define the location, change the location only. Save. Let's add another ring. So from Can1, let's add IR3, make it looks like R1 for a first stiffening ring. Just change the location, and here let's add the last one on this cone. So external stiffening ring, IR4, and same, let's make it looks like IR1, and from here just define the location, 300, 3100, and click save. Okay, now if we come back to the general arrangement, we have stiffening ring here on that shell. Okay, we have stiffening ring at that shell, which is the first shell after the expansion joint. So if we come back to the 3D model here, that's the expansion joint. So the first element after this expansion joint, which is can 5. So let's add a stiffening ring on this one. So it's SR2. Okay. And the same dimension, let's make it ring plate 80 and 12, and the location. Okay, so and click on start assembly to start creating the stiffening rings along the heat exchanger. Okay, after during that, if we come back to the drawing, here we have a saddle on this shell diameter, the large diameter of the shell. We have 4 nozzles, N8, N1, N6, and N7, which is a helicide nozzle, and we have a trunnion. And we have 2 stiffening rings, so let's add those elements. After that, we will add the impingement baffle here. Okay, that's the last stiffening ring. Now we create the stiffening rings along the vessel. Now let's add the elements on that can, which is the first can after the cone, which is can 6. So from here, let's open the SEG and select can 6. Okay, and from elements, let's add a saddle. So let's add saddle. Okay, and if we open the detailed drawings here, the right saddle, it's including 5 ribs, one on the middle, and 2 intermediate ribs, one on the middle, 2 intermediate ribs, and 2 outside ribs. And it's with a tight bottom width here. It's not with straight sides like that one. This one was straight side, but that one was a tight bottom at the end. So from here, let's select saddle, right saddle, and from here, let's select that type, which is saddle rib on the right side. And from here, let's define the saddle dimensions. The saddle height, okay, which is that value from the vessel center line. So the height, okay, and let's add wear plate. The wear plate, it's base plate, it's base plate, whole diameter, whole offset from the long edge, and whole offset from the short edge. Here, location, orientation, and from here that's the offset. Okay, as we noted here, the bottom width of the saddle, okay, we can get it from here. So we will remove the thickness of those outside ribs from here. So we will need to remove this checkbox and redefine the bottom width of the whip, okay, and defined that value 15. Here the top width of the saddle, the bottom width of the saddle. Let's add a mid-rib and intermediate ribs. So the offset between intermediate ribs, we can get it from here, which is 385. So 385, and let's click on save. Okay. Now let's add another nozzle to the same shell, which is N8. So when we come back to the model, let's add N8. So from here, let's select nozzles and let's add N8. N8, it's 2 inches, schedule 80 like that, and let's add a flange. So from here, let's add N8 flange. It looks like in 9, it's 2 inches. And from here, let's define the projection of this as per drawings. If we take a look here, the projection is 780. Okay, so let's come back here, 780, and click on calculate to calculate the projection of the pipe. Let's add another nozzle, which is N1. Okay, N1 is a nozzle from N1. If we check it here, N1 is 20 inches and with a thickness 10 millimeters. That means it's a nozzle from pipe. So from here, let's select a nozzle from plate, not from pipe, sorry, and that's the outside diameter of 20 inches. 10 millimeters, the longitudinal boiling line orientation here, the location, the same location of the saddle, the orientation at 0 degree. We have a reinforced bed. So if we check N1 here and calculate the outside diameter, it will be 75. It's 10 millimeters thickness, and let's click on save. So from here, let's add a flange. N1 flange, which is slip-on flange with 150 degrees rating and the offset. And let's come back to N1 to define the projection. So from here, let's define the projection. Yes, now let's add another nozzle, which is N7. Okay, N7 is a helicide nozzle. Okay, N7 here. If we take a look, it's a helicide nozzle with an offset 40 millimeters, and that's the projection. So from here, let's define N7, define the schedule, and from here, let's define the location. Define the orientation, which is 90 degree, and it's a helicide nozzle. Here, let's define the value. It's in clockwise direction. Let's add a flange, N7 flange, N7 flange, and it looks like N10, which is 2 inches. Okay, and let's come back here, and from the calculator, let's define the projection. Like here, it's 500 and so that's the projection of this nozzle. Let's add the last nozzle on this shell, which is N6. So from here, let's come back and add N6. Okay, and N6 is a nozzle from pipe, 8 inches with a schedule ATS, and the location of this nozzle is 435, and the orientation is 180 degrees. It's with a rebag 60. Here let's add a flange to this one. So in flange, okay, and from here select the size. Sorry, slip-on flange at first and select the size and select the offset. Let's come back to N6 and define the projection. And now let's start creating the assembly. To start creating the saddle and nozzles. During that, we need to some more elements here, like those stiffening rings on this shell and the trunnion. We will proceed, inshallah, after creating those elements. We will proceed with those 3 items. After that, we will add another stiffening ring here. At last, we will add the pass partitions on the bonnet and add nozzle N13 on N12. Here we have the assembly of the saddle, the second saddle on the large diameter. Okay, I think the location of nozzle N8, we need to modify it. nozzle N8 here. Yes, we didn't define the location. It's 185. As we discussed, don't make save during running. So we should wait or click on stop. After stopping and the activation of this button, we can click on save. Now, after making, that button become blue again, we can click on save. So now we can click save and update the location of nozzle N8. Okay, now it's in the right location. Now let's add the trunnion and stiffening rings, okay, and the impingement baffle. Okay, now for the trunnion location, we will select CAD 6, and from here let's select trunnion type 1, 2, and let's click on Add. Now after creating it, we will make it looks like trunnion 1. Okay, and make a refresh by moving to another node and come back to refresh the form. And from here we can define the location. So the location is the same saddle location, and click on save. Now let's add stiffening ring, 2 stiffening rings. We have 2 stiffening rings here, which is SR1 and another one here. Okay, so from here, from extension external attachments, let's add external stiffening ring. So from here, SR1, and from here, let's select ring plate, the height, and the location. Add another one, same can, which is SR3. So from here, let's add external ring SR3, and let's make it looks like SR1 because it's located on the same shell. So here, just we will change the location. Okay, save, and if we take a look here, we have an impingement baffle here. We will add an impingement baffle. So let's select CAD 6, and from internal attachments, let's add an impingement baffle. So it's for N1, so N1 impingement baffle. From here, let's select this one. As you can see, we have different types of available for the impingement baffles for nozzles. Okay, so you can select the suitable type for your case. In that case, we will make this impingement baffle and define the impingement and the width of that one. Let's make it 8 millimeters, the clip thickness, and the location will be the same nozzle location, and the orientation will be 0, the same nozzle location. And here we have support. Let's make it 8 millimeters, which is SW here, and click on save. Now let's click start assembly to proceed creating those elements. Okay, the last element here, which is impingement baffle. Okay, if we take a section inside this model to check the location of the impingement baffle, let's accept that section. Here that's the impingement baffle. It will be like that. Okay, for the nozzle. Now let's remove the section and let's complete the items. Here we have a stiffening ring on this small can, okay, which is the first can after the last cone. So from here let's select the first can after the cone and before the second tube sheet, and let's add a stiffening ring. So, okay, and from here ring plate, height, and location. Okay, and let's add nozzles to the last cone before the ellipsoidal head, so it's located on cone 8. So from here let's add N. Okay, if we take a look here on the nozzle table, it's half inch nozzle with a connected coupling. Okay, so from here let's make it half size, scalable standard. The location of this one, and let's click on save, and from here let's define the projection. Okay. And let's add a coupling to this one. So from fitting, let's add a coupling here in 13. And select the rating of the coupling, 3000, and the size of the coupling is half inch, and the gap between the end of the pipe and the coupling, let's add another nozzle in 12. Looks like N13 but with a different orientation angle. So let's add a coupling. After that, change the orientation. Okay, and make it looks like N13. If we come back to N12, we can change the orientation to 180 degrees. Okay, and let's click on Start Assembly to create the ring and the two nozzles. Okay, the last coupling. Now let's add the last element here on the drawing, which is the pass partition. Okay, so from here let's select the right head, and from elements let's add front pass partition. So right partition, and from here we will select 4 passes, that configuration, and let's define the right. If we take a section here to get the extension length from tools, we will measure from the facing of the gasket. We will measure from the facing of the gasket to the seam line here, so that value, 210. So from here, let's define this value. Okay, and offset, it's the same offset which we calculated from element. And let's click on save. Now let's start creating the assembly. Okay, now we have the bus partition on the rear end, like that. As you can see, if we take a look here, the gasket with the facing of the bus partition. Here we have the final model of the heat exchanger. I think we generated in less than 1 hour and 45 minutes. Okay. Now we will proceed with some items. We will add them by using the library of SEG, the external library of SEG, like adding tie rods to the model, and learn how we can do that. Learn to add manually. If we would like to make stud bolts manually to the model, how we can add it. After that, we can add some attachments like nameplate or something like that. But right now, let's start with the tube bundle. Let's take a section again, a half section here. Okay, and we need to add a tie rods. Two of tie rods will be on the short length, and two of tie rods will be with the long length. So how we can deal with that, and how we can get them from the external library of SEG. The first thing, to make the external library activated, you will need to open the SEG helper first. If you open it for one time, the external library will generated on the bus of Autodesk Inventor library. Here on the external library, you will find some sub-assemblies or some assemblies you can use it for the lifting simulation, like the telescopic crane with 50 tons, and some iLogic drawings for storage tanks. Okay, by opening this form for one time, you will be able to get the following, which is, if you open a new, click on a new button here on Autodesk Inventor, you will get this folder, which is SEG items template. And if you select tie rod and the ceiling rod, you will get those items. So we will open the tie rod. Okay, and you will need to open the iLogic browser. So if you haven't it, how to open it? From View tab, you can open the user interface, and from here you will select iLogic browser. So it will appear. It actually will appear like that. You can move it and drag it where you would like to add. So let's add it on the right side. So from here, from Forms tab, you will open the form and define the dimensions of the tie rod. So let's define the length of the small rod, and the length here, the thread length and at start. Okay, the rod diameter, let's make it like that, and the thread length will be 14. Okay, and let's click on save. So if you click save from here, you will not be able to save, because in that case, as we discussed on the previous session, SEG takes the control from Autodesk Inventor. So you will need to come here to the assembly tab and click on save active document. Automatically, when you come back to Autodesk Inventor, you will get this form to save this part. So we will name it as short tie rod. Okay, and let's save it and take a copy from it and make it the long tie rod, and let's open it and define the length of the tie rod. Okay, and click on save. Let's click on save and close. Now let's create a nut. So from here, let's select a nut, and from this form, let's open the nut form and define the nut size. It's the same end thread of the tie rod, which is 14, so we will keep it as it is. Just we will need to save it. So from assembly, we will click on save document to save it. So tie rod nut. Now let's create an assembly for the tie rod to make assembly easy for elements. So from here, let's open the standard assembly and let's import the short tie rod, and let's add a nut. So let's add the nut, which is tie nut rod, and from here, let's assemble this tie rod with the nut. Millimeters, and let's copy from this nut and paste here. So now we have this tie rod with nuts. To save it as discussed, you should come back to SEG and click on save active document, and when you come back, you will be able to that short tie rod, and let's assembly, short tie rod assembly. Save. And after saving, we can take a copy from it, which is the long tie rod assembly, and when we open the long tie rod assembly, we can make a replace for the tie rod, the short tie rod, by the long tie rod. So from here, let's replace this one and click save and close. Now when we open the tie rods from here, okay, we need to make the holes for the tie rods. So how we can do that? Okay, let's open the second tube sheet, because as you can figure, the tie rod is connected to the second tube sheet, not the first tube sheet. So we will open the second tube sheet, and on that face, we will draw the location of the tie rods. So let's add 4 tie rods, make those holes on the same, make them aligned horizontal, and those aligned vertical. And now let's add the location 350 from here, 150 for the bottom, the same, and for that one, let's make it the same from this one, and let's click finish. Now when you open on holes, okay, you will be able to make a thread hole. Okay, so if we select ANSI metric profile, select the size to be 14, looks like the end of the tie rod, and from here you can make it as a distance. So from here you can define groove and length of the thread. Now you have the tie rod locations and the threads on the tube sheet. Now let's click on save, click close. Now let's make the same on this baffle. So when we open this baffle, we can open it from here. The same thing we can do the holes. So from here, let's add 2 holes. Let's make them aligned in horizontal, defined same location. And let's make a hole. It's thread hole with through all. So from here, let's define the diameter millimeters. Save. Now we have the holes on the top baffle. Click save. On the second baffle, let's open the baffle from here, and let's create a sketch here. Let's add 2 holes for the baffle, and you can imagine how much time you will save in case of using SEG, and instead of making sketches manually. And here easily you can hit the tube holing with that arrangement in minutes, and instead of creating patterning and all of that manually. So we have here holes for the bottom baffles. Now let's assemble the tie rods. So if we add, let's take a section, half section here after this baffle, like that. Okay, now we have the holes here, and we can import the assembly of the short one. We will move it outside here and add another one, and by using the assembly button we will assembly that to here and there. And let's import that one. Okay. Same for the bottom, the long tie rods. So let's add them here, and by the assembly button we will assemble them. Same for that one, and click on save. Now when we change the section to make it, let's say, on the middle, like that, we will get the long tie rod and short tie rod like that on the baffle. The same thing we can do it with the spacers to add it to the model. For example, we will make one sample here. So we need a spacer on this tie rod on this area as a sample. So let's measure the distance from here to there, which is the distance between baffles from inside. So we need to add a tie rod with that length, which is 930. So let's open from new, and let's open SEG templates again, and from accessories you will find the spacer here. Let's open the spacer and open that form. Select the spacer diameter and the thickness, and from here we will define the length of spacer and click on save. By the way, you can change the color of this one as you like. For example, let's make it smooth yellow, something like that, and let's save it. So from here let's save document and spacer 1. Okay, let's close that one, and from here let's import the spacer like that. Okay, and let's move it outside because now it's on the section side, so we cannot see it. So it's here, but we take a section, so we need to move it a little bit. So let's move it on that side to be able to see it. Okay, so from here let's make, okay, and so it's the same size of the tie rod, so we can increase it a little bit. So from here let's select that surface and that surface to add the spacer. So let's open this spacer and modify the outside diameter. So let's select 3.1 and save. Click update. Now we have this spacer like that, and we can repeat it on the other baffles on the bottom up to here. So we can repeat it 3 times. Okay. By that way, we generate the 3D model of the heat exchanger with making all details inside. And here, as we discussed, we make a sample for the stiffening ribs, and we can add the same for the top nozzles. For example, if we would like to add a stiffening ring for nozzle N11, so from here let's select external attachments and stiffening ribs, so N11 ribs, and from here let's define the dimensions. So from here let's select this rib, and from here select other, like that. Define this value as 40 millimeters, 40, which is the offset of the and let's define the projection, get the projection of nozzle in 11. So here that's the projection 135, so it's reflected here. And sorry, we need to define the same location, by the way. So in 11 location, we can get it from here, which is 560, so the same location. And click on save. Now when we click on start assembly, we will generate the stiffening ribs for nozzle N11. Okay, by the same way we can add stiffening rings for those nozzles. So from here let's select the can one and let's add a stiffening rib for N10. Okay, and let's make it looks like N11, and we will change the location only. Another one, let's add another stiffening ring for N9. Okay, and let's make it look like N11. Here let's change the location for this rib as the same of nozzle N10, which is in 2010. So the location, and for N9 the location 3260. Okay. And let's click on start assembly. Okay, now we can, I think, after making the 3D model, we can make an open discussion if you have any questions. One more thing regarding the tightening bolts, we can do it the same by using the library of SEG. From here, let's open the bolt and the nuts, and from here, let's open the select the stud bolt, and from the stud bolts we can measure the required length from here. So if we measure the distance from here to there, it's so we can make it 320, for example. So let's change the length 320, the size to be 39, the knot spacing, we measured it from here to be, which is that distance, that's the knot spacing. Okay, so from here let's define that from the floor spacing. Okay, and let's save that as we discussed. To save it from SEG, from assembly, click on save document and let's create up the same from here, the knot size, and let's save it, save document. Okay, and let's create an assembly for the knot. So from here, let's select standard assembly, and let's open the stud bolt, import it to the assembly, and let's add the M39 nuts, and let's assemble them. Let's open the UCS, and from here select the start nut from here, and here the end nut. Sorry. Like that. If we measure the spacing between the two nuts, it should be the same spacing that we defined on the nut. Now let's save this stud, so from the active document, and click on save. Now let's close that, and on the assembly let's import the stud bolts. So from here let's add the stud bolt assembly here and there, and let's select that one from here, and from circular pattern let's select those and select the circular pattern and repeat them the number of bolts. So we have the bolts like that. Now to add the external items to the bill of material, to SEG bill of material, because right now we add them on the 3D model, but they are not reflected on SEG material. So how we can do that? So from SEG, from tables, we will open the bill of material table, and from a button here which is called extra bill of material, the first thing we should do after opening this form, we should select the vessel. So should select the vessel from here. After that, we will add the item number, and we should make a number greater than the last number here. So we could start from 100. So let's select the first vessel and select 100, and we have, let's say, 2 tie rods. Technical characteristics, let's say rod 20, and length 5. the material. Okay, and the weight, let's kilograms. Part name, let's add here as a short. Number, part number, let's add the number and let's save and update. Here we have short tie rod. Let's add the long tie rod, so it's 100 like that. Quantity we have 2. Description tie rod. Technical characteristics as the same. Anything, the material, anything, the weight, except the part number, long tie rod. Okay, now we have short and the long tie rod. We can take this description from here to here and modify it. And for the mass, for the material, let's save and update. By that way, you can add items to the bill of material. If you go below here, you will find the items that you define, which is the tie rod here and there. The same for nuts and the stud bolts. By that way, you can export those items to SEG bill of material in your drawing. One more thing to reflect is that item number here, which is 100 for the short tie rod. If we open the assembly, let's take a section here to open. Here we have the short tie rod. If we open it and open that tie rod, here if you open the form, you will find a number for the part number in bill of material. That number, if you defined it here, it will be reflected on the bill of material, which is the number of the tie rod here on SEG bill of material. That number, you will reflect it on the part number in bill of material. That will give you the ability to reflect the item number in your drawings. I think we can start the open discussion. If you have any questions, we can proceed with it. Here, that's the final model of the heat exchanger. Any questions?